I would say, what's in a word? What's in a name? Then we've had a snoop full of chemistry this semester already. Now we're going to talk about heat. Changes in energy, but in particular heat, that take place during a chemical reaction. Yeah, I don't want that. All right. We need some definitions first. You've probably seen this one before. Energy is the capacity to do work. Doesn't mean work's being done, just means it has the capacity to. Yeah. Kind of like certain employees I've known in my life have the capacity to do work.
I can do it, we can
So it all revolves around the conservation of energy. In other words, in any process, energy must be conserved. You can't create energy, you can't destroy energy, you can transform it from one form to another or one place to another. Although Albert Einstein did kind of show us that energy and matter are interchangeable with this famous equation. But for chemistry, that change in mass that can be related to energy that Einstein was talking about is so small it's immeasurable. It only happens in significant amounts when you get nuclear reactions. So for chemistry, we're safe. Another way of putting this is actually the first law of thermodynamics. And we'll look at that in more detail later. But what it says is the total energy of the universe is constant. It does not change. I think another way to put that, yeah, let's see. It's usually written this way. Change in energy for the universe is zero. In other words, there's no change for the whole universe. It's got a certain amount of energy and that's it. It just transforms. Okay. There are very few chemical reactions or physical processes for that matter that occur without some transfer of energy. It may be hard to detect the transfer because if the amount of energy is the same before and after, you have to have a way to detect the movement. And we already said that the total energy is going to be the same. So we have to see, all right, how do we detect that energy movement, transfer of energy? That's the key. All right, energy can be subdivided into two categories. Potential energy, and that can be energy due to position. In other words, and that's just what it means, potential. The energy is there, but we can't get at it yet, or it's not evident. It's potential. And actually that's a good thing because if there's potential energy there, we can figure out how to get at it, then we can extract it to use it. Like a ton of coal has so much potential energy in it if you burn it. But the one form of potential energy is due to position. So if I'm on top of a building and I want to get that energy back, all I have to do is jump off the building. And I'll get it back. I won't get it in the form I want it, right? Because I'll get it back in the form of kinetic energy. In other words, how fast am I moving when I hit the ground?
It won't last very long.
Yeah, I'll have a lot of energy until then. But this potential energy can be due to position, and that can happen in any gravitational field. So potential energy relative to what? Relative to the center of the Earth.
Yeah, so how much energy would the tectonic plates have?
Their potential energy?
They have to have a lot to create earthquakes and tsunamis.
Yeah, that energy is supplied primarily by
What big
heat.
Oh, heat.
No, it's heat from the inside of the earth.
Yeah, but then they smack against each other, so they also be kinetic.
Yes. There's these are, I guess you could say that's position, because when you get two plates sliding over each other, like you get this one plate sliding against another plate, and then it shifts. See, there's another plate here. Say that place is moving this direction, and this place is moving that direction. If they move smoothly past each other, then you hardly notice it. But if they build up strain, if they stick along that plate, and then the rest of this plate tends to, let's say, drag behind as it moves, and this one drags behind, you build up potential energy in that strain, and that's when it gives loose.
When it gives loose, when the earthquake would happen.
Right. Yep. And that can happen in numerous ways.
How long do they have to strain before we form an earthquake?
That's the $64,000 question. Nobody really knows. Predicting earthquakes, that's what you're asking. How long will it go before it snaps?
Because
Nobody
the
knows.
longer it goes, it's going to be the worse of the earthquake, wouldn't it?
Yes, stores up more energy because it's constantly moving.
It'd be bad if it's stored up for a day. I'd say some area wouldn't be there no more.
Yeah, and then the way that the plates move also determines the type of damage. If they're sliding, then sure, that makes a shake. But if they're, say, worst case scenario, if the plates are underneath the ocean and the strain is this way, and they go like that, and then they snap, what that does is that lifts that water above them. And then it drops, and you get a tsunami from there. Mhm. Okay, so we can position, for example, in a gravitational field. So you can have potential energy in around any heavenly body, right? Around an asteroid, probably won't store up very much. But around Jupiter, you can store up a lot of energy there. Composition. This is the one that we're primarily interested in. It can be chemical energy, which means, and for chemical energy, the energy is stored in bonds between atoms. You can have electrostatic attraction or repulsion. And technically speaking, that could be considered a type of chemical bond in the right conditions, like between ions. You can store up energy there. So it's either potential or kinetic, which kinetic just means it's moving. Right? So kinetic energy is if the temperature of the object is above 0 degrees or 0 K, then it's got kinetic energy of some kind. The molecules inside will be moving, or the whole object can be moving.
The higher the heat, the more that kinetic energy.
Yes, the molecules are moving faster, right?
Lower just sitting there.
And it all depends on that equation. It's related to mass and velocity. So think about it this way. If you're moving down the road at 30 miles an hour and you accelerate to 60 miles an hour, you've doubled your speed, but you've quadrupled your energy. So it takes, to go from 0 to 30, it takes a certain amount of energy. To go from 30 to 60, it takes twice as much, 4 times as much energy. So that can hit your pocketbook if you like to drive fast, or it can smack you in the face if you're going faster and hit somebody. Right? There's a lot more energy to be released. Okay, those are the two main types of energy. And there's often an interchange between these two. For instance, in this picture, which one has more potential energy? Well, A does, of course, relative to B and relative to the surface. So if A is being held here by some sort of glue or a pin or something, when we pull it out and let it go, it's going to it's going to change some of that potential energy into kinetic energy by the time it hits B. And then when it hits B, we're going to have a collision and a transfer of energy. And A was up here at this level before. And when it hit B, we're saying it transferred all of its energy to B, but B only made it this high. So that means it didn't transfer all of its energy to B. Some of the energy was lost. And where did it go? Friction. Right? Now, ideally, all that energy transferred would put B back up here, same height as A. So if you minimize friction, you never get rid of it completely. But if you can minimize it, then you can get almost all of your energy back. And that's the concept behind roller coasters. Right? It's a slow climb to the top. And then the precipitous fall off the end. And you convert that stored energy from the climb into motion. And you go down and around and over like this. And eventually yes, if you're going fast enough. Right? You got to be going fast enough so that, well, all right, technically speaking, you got to be fast enough so that the centrifugal force keeps you on the rail. But the way roller coasters are made, they got wheels on both sides of the rail, right? So they're going to hang on. You could stop like that, be hanging.
Yeah, I know, that probably freaked me out.
with cause, yeah, just cause there. All right. So I stuck this slide in here because it's easy to get these terms confused. Temperature and heat, they're related, right? And in fact, they're first cousins. They're related, yes. They're not exactly the same. With one respect, temperature is different than heat in that temperature is an intensive property. In other words, if you measure the temperature of something, you can measure the temperature of that object here or here or here. And if it's homogeneous in that temperature, it'll be the same temperature everywhere. Doesn't matter how much of it there is. That's an intensive property. And it's based upon the random motion of the molecules. In other words, one definition of temperature is that it is the measure of the average kinetic energy of all the molecules in the substance. That's what temperature is.
Yeah, because the more you move around, even the room's going to get more heated up.
Mm-hmm. Yep.
Is that why whenever you go up and down, where there ain't no kinetic energy, hardly it gets colder? Because the higher you get in altitude, the colder it's going to get. And the lower you go, the colder it's going to get.
Let me see if that's true for this. The air gets thinner. I think it has more to do with the insulating capacity of the atmosphere. Because the Earth is constantly radiating heat to space.
And the sun's constantly radiating to us just about.
Right, right. So generally, as you go higher, that's a good point. Temperature can be, actually, as you go up, it gets cooler until you reach a certain point, and then temperature increases.
Yeah.
But even though the temperature increases as a measure of the average kinetic energy of the molecules at that altitude, there are not that many molecules up there, right? So the heat is lower, whereas the temperature could get higher. And that's where heat, the definition of heat comes in. Heat is measured as a transfer of energy from one place to another based upon a difference in temperature. So that's where they're related. But heat itself is an extensive property or a capacity factor. In other words, the amount of substance and the difference in temperature determines how much heat there is or how much heat is transferred. And it's related to, often related to the mass of the substance, the composition of what is the substance made of, and the volume of the substance. Okay. So heat does vary with the amount, whereas temperature doesn't. I'll have to look that up, see why that is. I can call my brother. He might know. He's a pilot. So he's always going up there. He goes back down. He goes up there. Goes back down. Probably why he got cancer on his ears. You go up higher, you don't have protection of the
UV rays.
Yeah. Okay. So just to reiterate, heat involves a transfer of energy between two objects due to temperature difference. If they're at the same temperature, then there's no heat transfer. They're said to be at thermal equilibrium. Now, let's recall some more definitions. Right? What's the definition of work? It's, well, energy is the capacity to do work. So how do you measure work? Well, there's a physical definition for work. That's what I'm going to give you now. Work equals force acting through a distance.
So moving.
Something has to, right. When you apply a force to something, it has to move. And if that force is constant, then the distance through which it acts gives you the value of work. Right? So if work equals a force times a distance, what are the standard units of measure for force? Have we done that yet?
For force, no, but for pressure, it's Pascal.
Okay, we're going to get to that one too. Distance is meters, right?
Yeah.
Okay. Force is derived from Newton's second law of motion. Mass times acceleration. Okay. So if mass is standardized to kilograms and acceleration is meters per second squared, then force is kilogram meters per second squared. Actually, the SI unit for this is the Newton. Okay, so this is also Newton meters, excuse me. Newton meters is work, but we can't leave well enough alone. That's equal to a joule. Okay, so energy is in terms of joules, but they're interchangeable with Newton meters or kilogram meters squared per second squared. Those are all equivalent. So if you have to do a calculation where certain values need to cancel and units need to cancel, then you have the opportunity to substitute these units in there for it. Okay, that's work. So if I push on this board like here, you can measure the force. Right? If I had one of those bathroom scales with an analog dial on it, not the digital ones, but the analog. I think they still make them.
I think they do, but I've never seen them.
If I put one of those between my hand and the wall, you can measure how much force I'm applying to the wall. The wall's not moving. So I didn't do any work. But energy was being expended, right? So where did that energy go? Turned it into heat. Friction. I mean, yeah. Heat.
Against the wall.
Yeah, and pushing against the molecules and
It's making them move against each other.
so yeah, expended all that energy and not done any work. Okay. So there's also another concept that we need to work on. That's the difference between a state function and a path function. A state function says that previous conditions are irrelevant. Doesn't matter how you got there. The state is where you are right now. And if you're at this state and the path takes you over here and over here and over here like that, over here, that you end up at the back of the same state, then you haven't changed at all. You're still in the same state. Path doesn't matter how you got there. Whereas a path function does depend on on how you get from one place to another. Right. So with reference to our discussion today, energy itself is a state function. So if we say the system possesses so much energy, right? That value, doesn't matter how we got there, it just has that much energy. Whereas work, if I have to push something up a hill and I try to go, well, actually, if I try to deadlift it straight up, then that's a certain amount of work, right? The force, the weight of that mass times the force required to lift it is a certain amount of work that I did. But if I have to apply force and push that mass over here and over there, and then I go over here, and I go over there, I eventually get to where I deadlifted. But it took me 2 days to go that other path, and I'm still pushing. It probably takes more work to get there that way than it does to deadlift it. So work is a path function. It does matter the path that you take, like whether you go to Charleston on back roads, 2-lane roads, or whether you go on the turnpike. Makes a difference in how much energy you expend, how much work is done to get there. Heat is also a path function. There's another state function. We'll talk about it in just a minute. Oh, I got a definition. I should have just punched the button. It only depends on your present state. That's the state function. And a path function depends on how you got there. Okay, we need some more definitions also, because we're going to be talking about energy transfer, heat transfer in particular. We need to define some terms. So it's useful to define the system. And actually, the system is any part of the universe where you're focusing your attention. What does it take? How do we define our system this way so that we can solve that problem? If the problem's bigger than that, then our system needs to be bigger. The only system that is predefined is the universe. And the universe is technically a system with no surroundings. Okay. The system and then everything else is surroundings. Okay. If you're saying the universe itself, the whole universe, then there are no surroundings because you put everything in the system. So we rarely talk about things that way, except for that one law. The change in energy for the universe is zero. But for everything else, we always have a system and a surroundings. And we look at the transfer of energy or the transfer of heat in these conditions between the surroundings and the system. Okay, there's a boundary here that it has to cross to get to our system. Okay, so here I did a little animation. So here we have our system and our surroundings up there. Sometimes it's instructive and useful to limit the surroundings. In other words, say, all right, our surroundings only go this far. That's it. We don't care what happens elsewhere, just within this environment. So now we've limited the discussion to this system and the rest of the surroundings. And you can view this arrangement here in three different ways. The system itself can either be open, where energy and matter can both transfer freely between the two. There's some natural systems like that. Or you can limit it. You can say it's closed. Matter can't transfer. You can't send matter across that boundary, but energy can transfer. That's a closed system. Okay, and it's coming from the surroundings that we've limited to this space out here. And the other possibility is isolated. You can isolate the system so that neither energy nor matter will transfer. Okay. And the isolated system is the one we use in the lab when we study calorimetry. We'll talk about calorimetry in a minute. Okay. Now, when a reaction takes place, we speak of it in terms of which way does the energy move. If we define our reaction as our system, then does energy flow into the system as a consequence of the reaction, or does it flow out of the system when the reaction occurs? If it flows into the system, we have an endothermic reaction. Endo meaning into. Okay, heat flows into the system. It has to absorb energy from the surroundings. So if we've identified and limited the surroundings to this certain space out here outside our system, then the energy that flows, that ends up in the system, has to be equal to the energy that was lost by the surroundings. Okay? I guess in technical terms, if we limit the surroundings like this and our systems here, then if we're going to talk about these two and possible energy transfers, then this has to be an isolating boundary, right? Nothing gets in or out here. Otherwise, it doesn't make any sense. So heat flows into the system. That means it absorbs energy from the surroundings, like that. And that's endothermic. Everything is referenced to the system. So when we say endothermic, that means energy moves into the system. Okay? Exothermic is just the other way around. Energy moves out of the system. Okay. Let's see if we can identify endothermic versus exothermic for these processes. Oh, we got to define the system first. All right, so this is what you do. You define the system, define what the surroundings are, and then you say which way is the heat flowing. is, oh, freezing of water, excuse me. I read my own question. As water freezes, what happens? Well, it goes from a liquid, huh?
Heat goes out of it and gains goes.
Yeah, if we define the water as the system, right? Water here,
Kinetic energy, so it's gonna freeze.
it's got to lose energy, right, to turn from a liquid to a solid, correct? So it's an exothermic process. That's right. So in this case, we've identified the system with this underline. If your hand is the system, and we say it gets cold when you touch ice, right? Transfers energy from your hand, the system, to the ice.
The ice is gonna be in the thermos, the heat from the
If we switched it around and said the ice is the system, right, then we could call it endothermic. Oh, I didn't read the question first. Ice gets warmer when you touch it. Oh, it's just the opposite. Yeah. Water boils in a kettle.
So it's already telling you it's getting heated.
Right. You heat the water, so it's endothermic. You're transferring energy into the water. Water vapor condenses on a cold pipe.
So it's getting colder.
The water vapor
Yeah, so it's condensing, so it has to be getting colder.
has to be getting colder. It means it loses energy.
So it's
Exothermic. Yep. And then ice cream melts. Right. Okay. So let's see. Now, in this scenario, we have to define for ourselves what is the system and what are the surroundings. Right, so methane burning in a Bunsen burner. So what's the system? Well,
Oh, what's the system?
yeah, what's the system?
The system is methane and the surrounding is a Bunsen burner.
Right. The system is actually the chemical reaction itself. Methane and oxygen combined to produce carbon dioxide and water. Right. So this is the system, and the laboratory, the surroundings are either transfer energy from them into or energy out of. So it's exothermic.
It's exothermic. Or the methane is burning.
Yeah, methane plus oxygen yields carbon dioxide and water. That's not balanced, but when these combine, they get hotter. You can feel the heat coming off of them. That's exothermic.
Oh, because they're releasing it.
Right. Heat is leaving, and we use a small Q to designate heat. Water drops sitting on your skin after swimming, they evaporate. So what's the system and what's the surroundings?
The water drops is a system in your skin will be the surrounding water.
You can define it that way. Yeah. Water drops, and as the water drops evaporate, they have to absorb energy, don't they? So it's an endothermic process. Yep. Okay. Hydrogen gas and oxygen gas react violently to form water. Okay, let's look at it this way. Hydrogen gas and oxygen gas produce water. Well, at those temperatures, it's probably gas too. Especially have you ever seen films of the space shuttle taking off? Long time ago, yeah. Its main engines, 3 main engines were fueled by hydrogen and oxygen.
Oh, yeah, I remember learning that in middle school.
Yeah. And produces water. Makes a lot of energy. It's very exothermic. So if we're going to say that it's exothermic, that is, it produces heat.
Yeah, that's why the fire comes out.
Yeah. The question is, which side? We can speak of these sides of the reaction, the reactants versus products, as having a certain amount of energy content. So the energy content here of the reactants versus the energy content here of the product.
What the reactant have like more than once I forget what word was already. So I can't. I know what the word is. But that's
Well,
the word.
Yeah, keep going with that one. So that means if we're giving up energy over here,
Potential energy is gonna have more.
yes, more potential energy in this part of the system and less on this side.
That's what I was trying to say. But I couldn't get it.
Right. And the conservation of energy says the total has to be unchanged. So if we've got energy here and energy here, then that has to be equal to what was over here, which means this has more energy potential than this one does. Right. And that's typical of chemical reactions. Chemical reactions proceed in such a way that they produce a more stable system. Yeah, more stable outcome. Right. So water has the lower energy of these. Okay, what do we mean by thermodynamics? Thermodynamics, in this case, we expand the definition to include energy. Thermodynamics, the study of thermodynamics and its interconversions. The study of energy and its interconversions is thermodynamics. And dynamic just means change. We've already looked at the first law of thermodynamics, the conservation of energy.
Energy.
Yeah, right. There's in the universe, the change of energy is zero. Or you have to conserve the energy. If you've defined your surroundings like this and the system is in the middle, then everything that happens in Vegas stays in Vegas. If energy transfers in, it had to come from the outside. If it goes out, it had to come from the inside, and the total has to be constant.
You can't get rid of energy, you just change it to different types of it.
Yes, that's right. So when we say universe, we're talking about everything, everywhere, at all times. There's another concept to define how much energy is contained in the system. Right? And it's the sum of all the kinetic and potential energies that we can define for all the particles in there. That's the internal energy.
You can do something on Earth, but would the energy be different if you did it out in space? Because you'd be doing the same thing, but their surrounding would be a lot different because of the gravity. So like
Right. And the absence of an atmosphere.
yeah. So you'd be using more energy out in space. You'd be
To do the same process.
you'd have less gravity, but you'd have to probably less energy.
Well, that's a good question. But I don't have a good answer for it.
I was just thinking of that.
Yeah. I know that rocket engines perform differently at sea level than they do in a vacuum. In fact, they're more efficient in a vacuum. So what we try to do, what we have to do, is use rocket engines with very large thrust component, so that we can escape the gravity into space. But once you get into space, you can use a rocket engine with low force.
Yeah, or they can like interchangeably use force with like, propulsions, random propulsions for like certain times.
Yeah. Or if you want to go somewhere in the distance, it's probably more efficient to have an engine that burns slowly but it's very efficient, and just keep it running continuously.
Yeah.
You just
One
keep
action-
adding energy.
One action is going to lead to moving further in space than it would on Earth, because one little thrust of energy is going to move you further than what it would on Earth. Like say you kick it off, you just go here, but if you kick it off in space, you go there.
Probably because you've got other forces to fight on the surface of the Earth. Yeah.
So that means you be losing this energy in space. Well, I don't know, because you'd be doing the same action, so it'd be,
I know one that's been experimented with is the ion drive. So you take heavy atoms of a noble gas, usually like argon or krypton, and you have an energy source. Nuclear is a good source, and you create a charge difference between plates, and you inject charged atoms of these guys in between them, and they're accelerated from one plate to the other, and they spit out the back. And they're very, very efficient. So it takes very little of this material to produce a massive change in momentum.
so if they could use those in rocket science, they'd be pretty happy.
Yeah, they've been tested in space and they work. Yeah. Okay, let's see, internal energy. All right, so that may be the different definition, but how do we change internal energy? There's only two ways to change internal energy in the system. You change the amount of heat transferred into or out of, or you do work on the system, or let the system do work on its surroundings. Either way, or in combination, will change the internal energy of the system. So we need a sign convention for these values, because if we're going to do math with them, we have to know which way the energy is moving. I mean, is the heat moving into or out of? Well, if it's moving into, it'll have one sign. If it's moving out of, it may be the same magnitude, but it could be a different sign. Right? So we need a convention. Okay, so like I said earlier, everything is in terms of the system. What does the system see? If heat is moving into the system, it's a positive value. The system is gaining heat, so that would be positive. If it's moving out, it'd be negative. Okay? Same thing with work. If the surroundings are doing work on the system, then the work that's being done on the system is a positive sign. If the system is doing work on the surroundings, yep, it's negative. Okay, so now that we have that sign convention, we can move ahead with calculations. If it gained too much heat, yeah, I guess you'd have to define the system. Some systems are pretty good at holding heat. For instance, in power plants, that's why the nuclear power plants in the US have always been pressurized water systems, because you can heat water very high temperature as long as you keep it under pressure. Right? If you don't, then it'll flash into steam. But other countries have chosen to use other ways of heat transfer, like even liquefied metals, like liquefied sodium.
See, that's a good example, because sodium was the system, and it can't hold that too much. If you got too much more heat than it can handle, then it would melt. So that'd be like the heat point.
Oh, no, they do want liquid sodium. Yeah, they heat it until it liquefies and then heat it some more. It has a very high, we're going to talk about this in a minute, I hope, heat capacity.
Could it evaporate if you heat
Sodium.
it as liquid?
Well, yeah, you could, yeah,
Like any metal.
theoretically, yeah.
I probably would be happy.
It has a heat of vaporization.
What would that happen if metal was to evaporate?
It would be like any other gas.
Like,
Yeah.
if you did it too much and next rain came, would it like change the color of the rain?
Color of the rain?
Yeah, because it had like properties of the evaporation because it kind of turned to precipitation.
If a gaseous metal came into contact with water droplets, it probably dissolved in them.
Yeah, so like color.
Yeah.
Probably wouldn't be healthy.
No,
That'd
that's
be
a
pretty cool to see.
pretty good assumption. Yeah. It would be right. Okay. So, and heat is in terms of joules, right? And work is in terms of force times distance, which is Newton meters, but they're interchangeable, right? Newton meter is a joule, right? So and the reason I say that is they have to be equal, otherwise you can't add them together. And energy is in joules. So once you determine how much work is done in terms of joules, then you can add it together with heat and determine, did the system lose energy or gain energy, right? Because if one of them is positive, gaining heat, but the system is doing work on the surroundings, which is negative W. Yeah, which one's bigger? Mm-hmm. Exactly right. Okay. So these thermodynamic quantities that we've just been discussing are like any measurement. They have a number, a magnitude, and a unit of measure. Well, actually, they have three parts. It's not just a number, it's magnitude and a unit of measure and a sign. We need to know that sign so it tells us which way it's flowing, into or out of. All right, and I've talked about this already, so we don't need to hash that again.
Hey guys, it's Professor Dave. Let's talk about thermochemistry.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. A reaction can either be exothermic, one that releases energy, or endothermic, one that absorbs energy. This change in energy is represented by delta H, or the change in enthalpy for the reaction. For our purposes, we can think of the change in enthalpy as being the change in energy for the reaction, or the energy stored in all the bonds of the products minus the energy stored in all the bonds of the reactants. If there is more energy in the products, delta H will be positive, meaning the additional energy had to be provided, making it an endothermic reaction. If there is less energy in the products, then that additional energy was released, making it an exothermic reaction. Energy, which is the capacity to do work, can have many forms, like mechanical, electrical, chemical, heat, and so forth. And besides quantum mechanical exceptions, energy is conserved. That means it can change forms, like heat energy that evolves when the chemical energy in a broken bond is released, but it won't be created or destroyed. Heat, represented by the letter Q, is a trickier thing to define, but a good way to put it is that heat is the energy that flows between a system and its surroundings due to a difference in temperature. Heat will always flow spontaneously from an area of high temperature to an area of low temperature. For a system, Q will be positive if heat is being absorbed by the system, and it will be negative if heat is being released by the system. When temperature and pressure are constant, Q equals delta H, the change in enthalpy. When we discuss thermochemistry, we will discuss energies in terms of joules or kilojoules. Another common unit used by chemists is the calorie, which is equal to 4.184 joules. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not to be confused with the food calorie, which is calorie with a capital C. This is actually equal to a kilocalorie or 1,000 calories, also abbreviated as kcal. A thermochemical equation reports the change in enthalpy for a given reaction in stoichiometric terms. Here, the delta H listed is specific to the molar quantities given by the balanced equation. So if the number of moles of each substance as given were to react, the change in enthalpy would be as listed. To find the enthalpy change for a specific amount of material, just do some stoichiometry. If twice as many moles of material as are listed were to react, then the enthalpy change would also be twice as much as listed. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay. Professor Dave gave us some stuff here that we hadn't defined yet.
Yeah, I was looking for it now.
Yeah, we're going to talk about enthalpy in a minute. Their enthalpy and heat are related, but they're not exactly the same. But we typically, when we talk about chemical reactions and the energy released or absorbed during the chemical reaction, we usually define it in terms of enthalpy. So we're going to have to define that and learn how to use it. But first, we want to, let's see, follow this for a moment. I need to get my hard copy out so I can keep track of where I'm going. All right. This has to do, this discussion on these next 2 or 3 slides has to do with what is one way that leads us to a better understanding of how we can do work on a system, or how a system can do work on its surroundings. Because it has to be in terms of force times distance, technically speaking, to satisfy the conditions for work. So one way to do that is to define our system for a gas, because we know that unlike liquids and solids, gases are compressible. I mean, we can get a distance moved with a gas, but we can't with a solid or a liquid. So let's stick to gases for the time being. So if we go, this is our definition for work, like before, and these are other terms that we're defining. So let's say our system is this trapped gas in this cylinder, and we know that the cylinder is a uniform area, and if we apply a force to the gas, or if we allow the gas to apply a force to its surroundings, that would mean the expansion of the gas, like this. It would move up. Okay, so it's moved through a distance. Delta H is our D value, actually. So it's moved through a distance, applying a certain force. Okay, so there we have the work that was done here is force times distance. Like this force, and it's under pressure, right? So we can define the force in terms of force equals pressure times area, like this right here. Just solve it for force. And I'm going to do that also in the next slide, or the next animation. But work that is force times the distance, if that's true, then the distance moved with the force applied would have to be pressure times area for this gas. Pressure is force per unit area. So the force applied is pressure times the area right here. Okay. If the gas is expanding and it moves this distance, delta H, then there's our D. But D is in terms of area, is a change in volume. So a change in volume has occurred. And what's volume? It's height times area. So height moved times area is a change in volume. Okay? And the distance, if we solve that for distance, this height moved, this distance equals the change in volume divided by area. Okay? Now, if we plug these values in here for work, we can define work for this gas in terms of familiar quantities for the gas, in terms of pressure, area, and change in volume. Right? That's kind of off the bottom here. So work, if we plug those values in here and then solve for them, area cancels, and now we have pressure times change in volume. Actually, you can write this equation for a change in pressure too. So it's actually work is a change in pressure times volume, the total. But for reasons that you'll see pretty soon, we're holding this pressure constant. And then we have pressure times volume is equal to work. Pressure times change in volume is equal to work. All right. So now with the same scenario, here's what we get. Pressure times a change in volume. Let's see, we already know that. So for an expanding gas, change in volume is positive. Is that right? Yes. Remember my definition for delta anything. Delta anything is final minus initial. That's always the case. When you see a delta, it's final minus initial. So if the final is bigger than the initial, that means this is a positive value, right? Okay, so this change in volume is positive. So what does that say for work? Oops. There we go. Work is pressure times a change in volume. So if the pressure is constant at some value, and this is positive, then work is a positive value for the system doing work on its surroundings. Okay? So the system is doing work on its surroundings, which means what? Work needs to be negative. So we need a fudge factor. To make the signs convention work out, we need to say work is actually negative P times the change in volume. Now this convention aligns with that convention. So that's why the negative sign shows up in, that's why the negative sign shows up in this formula. Just to make things kosher. Okay. Now let's look at the units of measure for a second. There we go, like that, like that, like that. What are the units of measure here? There we go. If we say pressure is in atmospheres, change in volume would be in liters, right? So this work calculation is in units of liter atmospheres, not in units of joules. So if we want to use this calculation in some other, in a larger calculation, we've got to convert that to joules. So we need an equivalence. And here it is. 1 liter atmosphere equals 101.3 joules. Okay. So if you have a gas that's doing work or work's being done on a gas, you do this calculation before you can use it relative to any other heat transfer or energy measurement, you got to do this conversion. Okay, which of the following performs more work? A gas expanding against a pressure of 2 atmospheres from 1 liter to 4 liters. Well, let's see. P times V. Pressure is 2 atmospheres, and it's going from 1 liter to 4 liters. That's after, this is before, so it's 3 times 2 is 6, right? 6 liter atmospheres for the first one. How about this one? A gas expanding against a pressure of 3 atmospheres, and it's going from 1 liter to 3. So it's expanded 3 times 3 is 9. So more work has been done under these conditions. Correct? Did I do that right? Wait a minute. Expanding gas, pressure of 2 atmospheres, 1 to 3. Oh, that's only 2. 2 times 3. Yeah, they're the same.
2 times 4 is 8, 3 times 3 is 9.
So we've gone from 1 to 3, which is 2 liter change in volume. And this is a 3 liter change in volume. So 3 times 2 is the same as 3 times 2. Okay. Same amount of work. And if the value is negative, as we stuck this negative sign out here, the work is negative means that the gas has done work, the system has done work on its surroundings. Oops. An endothermic process that performs work. Okay. Now we have to say, what is the change in delta E in terms of its sign? Delta E is what? For the A situation, an endothermic process. So what does that mean for? Endothermic means the sign on this one would be positive, correct? And for this one, performs work on its surroundings.
So it works negative.
So that would be negative, right? Okay. Now we look at the magnitude. That's just the sign. The magnitude, if the work component is greater than the heat component, then that means this one would be negative or exothermic, right? Or a negative change in delta E. Right? And the other way around would be a positive change. For this one, work is done on the gas. So now this one's positive and this one's negative. Process is exothermic, right? Heat's leaving. So now if work is greater than heat, delta E is positive. And the other way around, delta E would be negative. Okay. Yeah, they can be tricky.
The next one is when we get into.
Okay. We talk about enthalpy. And we have to draw a distinction between Q and delta H. Delta H is a change in enthalpy. But enthalpy is more, think of enthalpy along the lines of potential. What is the potential heat from a reaction versus what actually transfers? Q is always a transfer of heat from high temperature to low temperature. It's actual what happens.
Just be like reaction in the product, basically.
Well, there is one condition in which delta H and Q are numerically equal.
Whenever it's
When the pressure is constant. Yeah. So very often, and that's why when a chemist studies a reaction, they'll generally try to maintain a constant pressure.
So it'd be,
So when you measure the heat transfer, you're also measuring the enthalpy.
so you don't have to worry about that one.
Right, right. Okay, and the other distinction between these two quantities is this is a path function,
Yeah,
and this is a state function.
because it's just another type of energy, right? Like you said, it was,
Right, it's measured in joules, yeah, just like any other energy.
you said it was potential.
It's a, yeah, what potential does this reaction have for producing energy?
So it's like a potential of a potential.
Guess you could look at it that way. Okay. So if we go back to our internal energy definition, delta E equals Q plus W. Q then is an actual transfer of heat, and W is the work. So if we look at them again, now, I can't explain why this equation, this is a thermodynamic equation. Enthalpy is equal to the internal energy plus any change in pressure times volume of a gas. So if there's no change in pressure volume during a reaction, then the internal energy change is equal to the enthalpy. But W is equal to minus P delta V. So if we solve, delta E is equal to Q plus W plus this one. Okay. And then what we want to do is say if the system, if the process is at constant pressure, then this is valid because that pressure is not changing, only the volume is changing. Then we can say this, right? We take the delta and put it inside and P, bring the P out as a constant, doesn't change. Then if we say W equals negative P delta V from here, we put that into the equation right here. Q minus P delta V plus P delta V. Then this one cancels, these two terms cancel. And under those conditions, yes, that's why delta H, enthalpy equals Q with constant pressure. Okay. It's easy to get the two confused. I'll have to admit that. Oh, so where have we seen this before? Just recently. Combined gas law, except this one doesn't have moles in it. It's got PV and T. Thought you were done with that, didn't you? No, it come back to haunt you. So there are a whole host of different paths you can take between the two states of PVT1 to PVT2. Along each of those different paths, values of Q and W will differ. Those are path functions. No matter what path you take, though, the change in enthalpy will always be the same. No matter how you get from here to here, delta H is a state function. And that's useful. Delta H as a state function is extremely useful. Because if it doesn't matter how you got from one place to the other, say in a chemical reaction, right? If you and you want to know what is the delta H of that reaction, what's the enthalpy of that reaction. But you don't want to perform that reaction because it's either too expensive, it's potentially hazardous, you know in advance that it might be extremely ectothermic. So you want to calculate the delta H for that. But you do know the delta H is for several other equations. Since this is a state function, you can add these up. And if their total of these equals that reaction, then you can also add up the delta H's. Yeah, that's Hess's law. We're going to look at it in a minute. Let's see. I got enough time. Yeah, I've got time. So another way to determine the delta H is that way, but it's also in terms of what's the delta H for the products and subtract the delta H for the reactants. So these have a delta H for products and these have a delta H for reactants. And if you subtract this from that, that'll give you this one. Now, the trick is, how do you know what these values are? And hopefully we'll get to look at that. It's important, right? Just remember that if our first pressure is different than our second pressure, then that sort of falls through. That means delta H is different than the Q.
So we would always love to have the pressures be the same.
Yeah, yeah. You can still calculate delta H. You just have to realize that the delta H from here to here is going to be different than the actual heat.
You just have to remember that.
Yeah. Okay. Let's see. Let's take this example. Everybody does this one on game day, I guess. You know, barbecuing with your propane grill. That's propane. We're going to burn propane and make carbon dioxide and water and produce this much heat, right? Negative sign means exothermic. Okay. And this is kilojoules per mole of propane. And this is a balanced equation. So for every mole of propane that is consumed, we generate 2,221 kilojoules of energy. That's a lot, a huge amount. So let's calculate the delta H if 5 grams of propane is burned, where oxygen is in excess and we're at constant pressure. So that's a fair assumption, because if you burn it out in the open, it's atmospheric pressure, and that's not changing. So we can make that assumption that the pressure doesn't change. So how would we deal with this? This is another stoichiometric problem, right? 5 grams here. So if this is in terms of moles of propane, all we need to do is convert that to moles, right? Use the molar mass, convert that to moles, and then use this as another conversion factor for moles. Multiply that times moles, and this in the denominator cancels moles in the numerator, and we end up with kilojoules. Okay, so there we convert to moles of propane. It's not many, it's 1/10 of a mole. Then moles times this per mole cancels moles and leaves us with energy. Just like that. And 5 grams of propane will give us this much energy. 252 kilojoules. Okay. Oops. So calorimetry. Now we're going to look at how do we measure this heat transfer. Right? And that's calorimetry is the study of the heat transfer from due to well, actually, it doesn't have to be a chemical reaction. It's just the study or the measurement of heat movement. There are 2 terms. Well, actually, every substance can if you add the same amount of heat in joules to different substances, they will change by a different number of degrees temperature. Okay, that's known as heat capacity. So if I have a substance here and I put so many joules into it, say 100 joules into this substance, its temperature will go up this much. But if I have a different substance and put the same amount of heat into it, its temperature might go up that much. Right? Different heat capacities. And if you have more of the substance, the first substance, and you put the same amount of energy into it, its temperature will rise only a little bit. So heat capacity is an extensive property. It's a capacity factor because it varies with the amount of substance. That's not very helpful. We need something that is intensive property that will not change with the amount of substance. And that's where we need specific heat capacity. So if it changes this many joules per degree Celsius, then that's heat capacity. But if we can find a way to measure it changes with so many joules per gram, it changes that many degrees Celsius, that's specific heat capacity. Now, you can have as many grams as you want, and this value will not change. If we, rather than grams, we use moles here, that's molar heat capacity. So it would be joules per mole degree C. Sometimes that's more useful depending on the units of measure that are spit out of a process. This may be more useful, or the other may be more useful. Okay, so if we have two reactants at the same temperature mixed and the resulting solution gets warmer, this means the reaction is exothermic. That's just logic. If it gets warmer, that means it's producing heat. So that's exothermic. An endothermic solution under these conditions would get colder. It's taking heat from its surroundings. Oh, Dave's going to talk again? Let's hope he doesn't talk too long. He's eating up my time. Here we go.
Hey, it's Professor Dave. Let's talk about calorimetry.
He knows a lot about the science stuff. Professor Dave explains.
Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water, and the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water to the final temperature in the coffee cup. So you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
So, instead of coffee cups, when we do this, it won't be next week, but it'll probably be 2 weeks after that. We'll do the calorimetry lab.
Because next week you have different.
Yeah, we're going to do the heats of waters of composition and hydration. So the construction, and this is the way ours will be constructed. We'll actually have 2 styrofoam cups. We want to insulate this environment in here from the surroundings. We want this to be our system that is isolated. We're going to isolate the system. That means,
The
yeah.
surrounding will be the styrofoam cup you put in that.
Well, okay, that's a good point. The styrofoam, right. The styrofoam does have a certain heat capacity of its own. So we have to compensate for that. Right. So anything we do in here, we have to say, how much heat does this styrofoam cup absorb? It won't be much, but it's significant when we do our calculation. So we'll take that into account. And then we have a thermometer in there, which also has its own heat capacity. I used to have a stirring wire in there, but that just is too much trouble. Plus, it was made out of metal, and some of the reactions we had will corrode the metal, and it was influence the reaction. So now I just leave that part out, and I use the thermometer to stir it. Okay, so the idea here is that what happens in Vegas stays in Vegas. In other words, the chemical reaction takes place inside this container, and whatever happens in there has to add up to 0. Right? There's no transfer of energy. So whatever's in there has to be 0. So anything that happens inside, if there's a heat change from one system, plus a heat change from another one, plus a heat change from another one, we can identify various components inside that calorimeter. Then we can identify these for each one. Like this might be water. Right? We've identified how much water is in there. And then we put something in there that will react, and that will be the other one. Like this will be the Q for the reaction. And this might be the Q for the calorimeter, right? So we can include that in there too. And all of these terms have to add up to 0.
So they're gonna be negatives in there.
There might be some negatives, yeah. Just so we end up with 0. Exactly right. This is an isolated system. Okay. So that's what I said. And this is it in blue lettering. And you can have as many terms as needed to identify each section of the components, the reactions inside that isolated system. Now, you saw two forms of heat calculation. One was that big C times the change in temperature. This is heat capacity. This was the first one I described. And then the second one is specific heat capacity. And then we take into account the mass and the change in temperature. Okay. We use this one for, say, we have water. We know what the heat capacity, specific heat capacity of water is, and how much of it there is, and then the change in temperature. Right? And like I said before, delta is always final minus initial. That's where you get the negatives. If the temperature increases, it's a positive delta T. If it decreases, yeah. Now this value, see, this is going to be degrees C, this is going to be grams, and this is going to be joules per gram degrees C. So numerator, numerator, denominator, denominator, those cancel. We have joules.
So unlike the other laws, we're going to be able to use Celsius instead of Kelvin.
And yes, in this case. Actually, sometimes these specific heat capacities are reported in terms of K. But it doesn't matter because the size of the degree is exactly the same. Now for this one, for the calorimeter, it's going to be not joules per gram degree C, it's just going to be joules per degree C. And then this one is degree C, those cancel, leave us with joules. The thing about this is an intensive property, this is an extensive property. So once you determine what this C is, and you do that, we're going to do that as the first step in our lab. Once you determine what the C is for your calorimeter, you can't change any of the components of your calorimeter, because if you do, it'll change that. Okay. But this, this is specific, you can play around with it. Okay. Let's see. How are we doing? How many more slides do I have? So how long can I talk about each one? We're going to do this calorimetry, and then we're going to look at Hess's law, standard enthalpies. I better move along. Okay. 100 gram sample of water at 90 degrees is added to a 100 gram sample of water at 10 degrees. So what's the temperature going to be?
Make it go lower.
This one will go lower, this one will go higher, right? When you mix them together. Since they're equal masses, then they should meet in the middle, correct? So we should have 90 plus 10 is 100 divided by 2 is 50. It should be exactly 50 degrees. That's an easy one. The trouble arises when you use different amounts of each one.
That'd be something I ask you, let water be warm whenever you're trying to.
Yeah. 100 gram sample of water at 90 is added to 500 grams at 10. So qualitatively or semi-quantitatively, where will it be, right? You've got less amount of this temperature than you do at that temperature. So it should be, instead of 50, it should be less than 50, right? Right down here. Now calculate the final temperature of the water. I don't think I have that in the slide, so I'm going to have to do it on the board. Yeah, I just got the answer. So let's see if I can get that answer. So the total is going to be 0, right, in our isolated system. So the Q of the hot water plus the Q of the cold water should be 0. Okay. So what is this one going to be? It's going to be S M delta T. This one's going to be S M delta T. Actually, different ones, different masses, and actually different changes in temperature also. But the S will be the same. And that was what, 4.186? I think 4.8, 4 point, what was it? I can't remember my specific heat for water in those terms. Oh, I know where it is. Useful information. Here it is, 4.184. This is 4.184 joules per gram degree C. Right there. Be the same for both of them. This mass, the hot water is going to be 100 grams, right? And cold water, wait, this is cold. The mass for the cold water is 500 grams. Delta T. Delta T is final minus initial. So what's the final temperature? That's the question. That's the unknown. So T final is the same for both of them. Minus the initial, so the 100 grams is 90. And the cold water is 10. So T final minus 10. There you go. So where's my calculator? All right, so we're going to have 4.184 times 100 times TF minus 90. Let's do that first. 4.184 times 100. I'm leaving out the units of measure. Times TF minus 90. And then we're going to add to that 4.184 times 500 times TF minus 10. Okay? So this is going to be 100 times 4.184 times TF, or 418.4. 418.4 TF minus 418.4 times 90. Right? Or 4 places. 37,656. Okay. Then we're going to add this one, 500 times that one. I can't do that in my head. Yeah, it's going to be 2,092 TF, and then minus, let's see, did I do these right? There. That's a minus, okay. This is a plus times TF, and then this one also times a minus 10.
Might just be negative
20920, right? Times 10.
How is that times 500 to make the same thing? Oh, because never mind.
I added a 0 because this is 10. Okay. So now we combine terms, right? So we get these two together. 418.4 plus 2092. So that's 2,510. 2,510 TF. These are both minuses. So let's say 37656, change the sign, and then 2092. I'll say 7656. Enter, and then 20920. So it's minus 58,576. I sure hope I'm doing this right. There we go. Now, if we put this one on that side, exactly right. So this one goes on that side. Now it's positive. divide by that.
That's the only kind of math I can do.
And that's rounded off 23 degrees. TF equals 23.3.
23 is the answer.
3 significant figures, that's okay. 3C. There it is. So it seems like a lot of work, but it's really simple. I mean, once you understand that,
Just algebra.
yeah, it's all equal to 0.
That's literally the same as that kind of algebra we're doing.
Oh, you're in the middle of this right now?
We did last week. We passed it.
Okay. It's fresh.
Yeah. I learned how to do that a long time ago. I like that kind of math. That's the only kind I like how to do it. It was easy.
Yeah. Yeah, it's just got one unknown you have to solve for.
Yeah, just solve for it. I like unknowns. You just solve for them for easy. Variables.
You need special rules sometimes. If your equation has powers or logs in it,
Yeah.
then you gotta do some fancy footwork.
Extra steps.
Yeah. Okay. Let's see. We might not spend a lot of time on this one because it is the same process. We'll just describe the scenario. Styrofoam cup with 50 grams of water at 10 degrees C, and you add a 50-gram iron ball at 90 degrees to the water. Okay, water is, we left off 4.184 is for the water, and then 0.45 is for the iron ball. So you would have your Q for the water, your Q for the iron with different S values. By the way, if this is 4.18 joules is required to raise the temperature of a gram of water 1 degree, how does that compare with iron ball? 0.45 joules is required to raise the temperature of a gram of an iron ball to 1 degree. What's the ratio of those specific heats? It's about 10 to 1, isn't it? Yeah, 4.18 divided by 0.445. So what that means is the heat capacity of water is 10 times greater than it is for iron.
So it's the
Uh-huh. So the same amount of energy applied to water will raise it 1/10 of a degree, whereas this one might go up a degree. The heat capacity of water is very high. And this is typical of most metals. Metals don't have a very high heat capacity.
They don't like hot stuff very well, do they?
And then even lower heat capacity. Have you ever seen the video of those ceramic blocks that they used on the space shuttle? They're very, very low heat capacity. They use a blowtorch and the thing's just hot. It's glowing. And the person goes in there with bare hands and picks it up by the corners. It's got a high temperature, but no heat.
But like, it's really hot, you just can't feel any heat anything off of it.
Right. That's the difference between temperature and heat.
So what if you touch the part that was glowing, would that break it?
It might if you hold it long enough. Right. Okay, the final temperature of the water is what? Well, we don't have time to do that calculation. You just do it the same way we did the others. Between 10 and 50. Yep. Okay. Hess's law. As I mentioned earlier, since enthalpy is a state function, you can take the enthalpies of several equations and add them up to your target equation and determine what the enthalpy will be for that equation. But you need some rules, of course, because the equations that have the known enthalpies may not be in the proper form. You may have to flip them, or you may have to multiply them by a constant of some kind.
Make sure they're all the same.
And that's one of the rules. You have to, when you add them up, they have to equal your target. Then you can add the enthalpies together. Okay, so why would we want to do it?
It sounds like you're finding the mean.
I'm sorry?
I said it sounds like you're trying to find the mean. I don't know if it's the mean, I forget which one was median or something, or we had to add them all up, that was right.
Add them all up.
Yeah.
Oh, that's the mean, yeah.
But you just don't divide by mean.
Maybe you can't afford to conduct the reaction. You don't have the equipment to do it, but you still want to know something about its enthalpy. So you can do that calculation, find out what it's supposed to be.
So you can just like get random calculations, and if they all equal that, you can find out what the enthalpy is.
You can, let's call it a prediction. You can predict the enthalpy of
But you won't not be exactly right, you'll be around it.
very close, yeah. Or it might be that earlier scenario. It's a hazardous reaction. And you want to know just how hazardous, how much energy is it going to produce? So instead of putting 2 liters together in this reaction, which would destroy the lab,
Yeah, see how far you need to run away first.
we put, yeah, you put just a tiny amount together. Again? Okay. Easy, yeah. Professor Dave.
Professor Dave here. I want to tell you about Hess's law.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemical equations can be manipulated to give important data about chemical reactions. We can use them to predict exactly how much energy will be absorbed or released by a reaction, which is very important because we don't want any unexpected explosions. There are 2 ways we can use tabulated thermochemical data to calculate the delta H of any reaction. The first way requires that we manipulate thermochemical equations in specific ways. So let's be aware of some rules. First, if a reaction has a particular delta H, the reverse of the reaction will have the opposite delta H or the same number with reversed sign. Second, if molar quantities in the equation are multiplied by a coefficient, so is the delta H. So if you double all the substances, double the delta H. These are things we can do to thermochemical data to be able to add equations together to result in a reaction we are curious about. Here's what I mean. Let's say we want to know about the change in enthalpy associated with a reaction, like this one. But it is difficult to measure experimentally. We can take other reactions with known enthalpy changes and rearrange them to align with our equation and get the data we want. The first reaction provided has carbon graphite on the left, which is where we want it. But the equation we want has 2 moles of graphite, so let's double this one. We get 2 moles of everything instead of 1, and we double the delta H. Next, this other one has CO on the right, where we want it, and in the right amount. So all we need to do is add these equations together. The O2 and CO2 will cancel because they are present in the same amounts on both sides, and we are left with the substances in our original equation. Since we added the equations, we also add the delta H's to get the delta H for our equation. This kind of manipulation is allowed by Hess's law. We can manipulate the coefficients of a reaction or reverse its direction in any way necessary as long as we change the delta H associated with it in the appropriate way. Then we add or subtract the equations as necessary to give us precisely the equation in question. The delta H you get by doing the arithmetic will be the delta H for the reaction. Another way to calculate an unknown delta H is to use standard enthalpies of formation. This is denoted by the following symbol, and it represents the enthalpy associated with forming 1 mole of a substance from its respective elements in their standard and most stable state. Most stable state means the most common allotrope, or physical form of an element. So carbon graphite instead of diamond, diatomic oxygen instead of ozone, and so forth. Standard state just refers to standard temperature and pressure, which is room temperature and atmospheric pressure at sea level. That's what is meant by the degree symbol. We can calculate the change in enthalpy for a reaction by adding up the standard heats of formation of the products and then subtracting the sum of the standard heats of formation of the reactants. The heats of formation can be found in your textbook or online, and you just plug them in, multiplying each value by the coefficients in the balanced equation. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, so we're going to talk about that in a second, the heats of formation, and adding those together and subtracting from reactants, subtracting the products from the reactants. It's all based upon the fact that delta H is a state function. That's why both of them work. So in this case, let's see, what do we have here? Oh, right, here's an example. Right, we have, this is our target, is this our target equation? I see what we're doing. We're comparing. If we actually do this reaction and measure the enthalpy, we get that value. Right? But if we take this equation, which produces a different product, NO instead of NO2, and we take this one, which takes NO and reacts it with oxygen and makes NO2, then if we add these together with these enthalpies, we get the same value as if we had done the measurement ourselves. Okay, this is a pictorial representation. This is why Hess's law works, because this is the energy of the reactants. This is the energy of the products. And in one step of the reaction, one of those reactions, the two reactions we add together, one of them goes this direction for a little bit and the other one comes back that direction. We end up in the same place.
I must learn something. My head hurts.
Okay. So how do we, suppose we have to rearrange the equations, right, in order to make them add up to the one we want. If you have to invert the equation, you just change the sign on your enthalpy. Right? If you have to multiply the equation by a constant, then you multiply the enthalpy by that constant also. And if you do both of those in whatever situation, then you add those modified enthalpies together, you get the target equation's enthalpy. These are examples. We're not going to go through them because of time. Let's see. These are the possible equations that we have. And notice in this case, we have fractionals. what that means is it's still balanced. It's just, it's not the way we learned it earlier, like whole numbers. But whenever, I'll make this point also, whenever you see a delta H out here with no denominator, like it just says kilojoules, that's how many kilojoules are either created or consumed or absorbed for this reaction in its present state. So it can be written in terms of 46 kilojoules per mole of ammonia consumed, or it can be 46 kilojoules per 3/2 mole of hydrogen gas. Right, either way. So you stick in the denominator that you need. All right. So when you're solving this type of a problem, a Hess's law problem, work backwards. Go to the target equation and say, all right, what do I need and where do I need it to be as a reactant or product? And maybe your instructor is devious and he gives you a problem with a list of like 10 equations, but you don't need all of them. You look at the target equation and say, which ones of these do I need to solve the problem? And then you say, all right, reactants and products. Which equation has the reactants in the proper position? Do I need to flip one? Okay. Do I have enough of the reactant or product? Right? You might have to multiply by a constant and then just follow the rules before you add them together. And if you add them together, then they have to equal the target equation. Right? So that's what we've done here. Whatever's required, multiply these by constants, then add them together. And once you do that, you can add up these values and you end up with that value for this reaction. Now, what do we mean by standard enthalpies of formation? The standard enthalpy of formation is best looked at in terms of, well, standard states. Professor Dave said one at sea level, pressure, and room temperature. That's not specific enough. When you're looking for this value for any compound, that 0 means 1 atmosphere and 25 degrees Celsius. Okay? If there are any solutions involved, then they have to be 1 molar. Okay. Those are standard conditions. Now, we can define this delta H. What does it refer to? You take the compound, let's use ammonia. If we're going to form ammonia, and we want to know the delta H for that compound, you have 1 mole of ammonia is your product. In its standard state, which would be a gas. Okay. Now we work back. What can we use to form that? To form that in its standard state, we need elements in their standard state. Nitrogen first, right? Nitrogen gas and hydrogen gas. Okay? You always leave this one alone at 1 mole. It's always 1 mole and you can't change it. So that means you have to use fractionals over here. So we need 3 hydrogens out of 2. 3/2. 3/2 of that hydrogen molecule will give you 3 of these. Right. You have, there's your hydrogen molecule. So if you have 3 of those, how many hydrogens do you have? 6. Right? 3 times 2 is 6. Well, we're going to take half of those. Gives you 3. That's another way of looking at it. That's the chemical way of looking at it. Mathematical works too. We need 1 nitrogen. So that means 1/2. Okay, so if you ever have to look up, if you have to go to a reference manual and look up the heats of formation for any compounds, that's what they're basing it upon. This is formed from elements and fractionals are required, usually. And then this delta H will be a value associated with that. So once you know this, then you can determine the delta H for the reaction. If you modify this to suit your Hess's law addition, and delta H is a formation for products minus reactants. So those are standard conditions. Near. And this is probably more information than you want. This says reactants make elements and then elements make products. These are the rules, right? We've already talked about the rules. Here you go, enthalpy calculations based upon standard heats of formation. So if you have a reaction, let's see if we can find an example instead of talking about it. Here we go. Here's a reaction between sodium and water. It's very exothermic. You throw sodium into a swimming pool and it'll explode. Potassium's better, though. It's a more violent reaction. Throw a banana in there? Oh, okay. Now, wrong kind of potassium. So sodium and water make sodium hydroxide and hydrogen gas. That's the destructive part. It makes hydrogen gas, and there's so much heat produced that when the hydrogen meets the air, there's enough to ignite it.
Well, that would be bad if it was the same kind of potassium using a banana and drop it in the pool.
So we have these standard heats of formation for all of these reactants and products. Notice that for elements, the standard heat of formation is 0. That's by convention. It doesn't take any heat to form an element. That's your starting point.
That's what for chemicals it will. That's what
Right.
it will.
For any compounds, there will be a value, correct? So we can ignore this one and we can ignore that one. We just need this one times 2 minus that one times 2. So 2 times this one minus 2 times that one, which would make it plus. And you get minus 368 kilojoules for that reaction. But we always have to consider that coefficient. Okay. Let's see if I can do this without climbing too high up on my soapbox. We start talking about fuels. And the one thing that just gripes my cookies to no end is this Green New Deal coming out of the leftists in Washington. The Green New Deal, that they're fashioning it after their favorite socialist from the past, Franklin Delano Roosevelt.
You don't need wood or something for fuel.
They'll send us back to the Dark Ages. That's their plan. Yeah, right. First of all, everywhere that sustainable energy sources have been forcibly imposed upon a society in every country around the world, their quality of life has gone down, their ability to produce energy has gone down, and rolling blackouts will follow.
Yeah, well,
California is-
blackouts anyways.
Huh?
We have a lot of blackouts around here anyways.
For different reasons.
Yeah, for different reasons, but we still have a lot of them.
California, they've tried to do this green energy thing, and they're experiencing the consequences of their folly. They have rolling blackouts.
I feel like California is an experimental place that they go with all the time. Like they try everything that's new before anyone else does.
Right, and most of the time it fails. Let's see, what did I hear today they were trying to do? They're going to pay drug addicts not to use.
That's not gonna work.
No, they're gonna take that money and go buy drugs with it.
They're gonna OD is what they're gonna do according to how much money they give them.
Yeah. Okay, so our present sources of energy include fossil fuels, which is the lion's share of all the energy worldwide. Right, we have pockets of differences, but worldwide, fossil fuels are still king.
Yeah.
Coal, natural gas, petroleum. Yep.
Are they still trying to shut down coal mines?
Always, as long as the Democrats are in control, yeah, they'll keep trying to do it.
It's gonna work if they keep it up.
Yep.
Sadly,
And then for centuries, wood was the primary source.
well, you can make charcoal out of it, so
Yeah,
it's like the closest thing to coal you can really get.
you can, right. In fact, that was originally the form of the coking process was made from wood. And then they discovered a more efficient source material was coal.
I think I could go outside and look behind my house and probably just punch the cliff side, and I'd say a piece of coal probably fine.
Uh-huh.
Because I looked out there and I looked in the rubble sometimes. And I just look over a piece of coal sitting there.
Yeah, yeah. And that's interesting. On my way over here from Beckley, there are lots of road cuts. And every road cut cuts through a seam of coal.
Yeah. There's always coal. Everywhere you go around West Virginia, you'll see that.
I guess it just depends on how thick the seam is, how deep it's buried, whether it's economic to get
I've
at
been walking through the creek and I'm pretty sure I saw a piece of coal just in the creek.
it. Hydroelectric power is useful, right? But in this country, at least, we've exploited about all the hydroelectric we can. You need a large drop in elevation so that you can build a dam and you can get enough head pressure to drive your dynamos. Nuclear, no. Nuclear is the answer, right? If you're really concerned about carbon dioxide pollution, which is really not a pollutant, but let's give them that argument for the sake of this one. Nuclear.
Humans, but the thing is that we don't really do anything because we don't breathe out enough. Then the trees produce oxygen, it's like carbon dioxide. So.
Yeah, that's right. For green plants, carbon dioxide is food.
Yeah, so they eat a little more than that we can get out. They produce more oxygen for us.
And the ability of the oceans to absorb excess CO2 is massive.
Yeah, there's more water on Earth than there is land, so we really don't have to care about it.
Yeah. But if you ever get in an argument with a leftist who's trying to squash fossil fuels, and they want to go with green energy, just ask them what's their position on nuclear energy.
I probably don't know anything about it.
Right. Either they don't know or they don't want it either, which means they're a fraud because nuclear will eliminate all of these.
All the bad side effects.
Yeah. Right.
Except for it's just highly dangerous.
The problem in this country with nuclear power is that somebody made the decision along the way to use pressurized water as the transfer medium for the heat. That is a mistake. That's why all the nuclear plants have these huge, you see these huge domes?
Yeah.
And the reactor is this little bitty thing down here.
That has to be dangerous.
Well, the reason for that dome is if this pressurized water springs a leak, it instantly flashes to steam, which is 1,000 times as much volume as the water. You need a big dome to contain it.
Well, I remember telling you about that one foreign film I saw, and it was like something like a nuclear reactor, but water leaked, and it caused a bad nuclear reaction all around the whole area. People had to leave that area for a while.
Yeah. And they're still working on Chernobyl in Russia. It's going to be a hazard for hundreds of years.
I think someone said they went fishing there, like in a video, and they caught a catfish in the river right next to where the explosion happened, and it looked funny.
Yeah. This is just historical significance, right? We started off with wood, then we moved to primarily coal, and then natural gas and oil started kicking in. But we're still significantly coal-oriented and fossil fuels. Right? Some countries have gone nuclear, and they've used a different reactor design than we have, and they're successful at it.
Yeah, it's probably better.
Yeah, yeah. In fact, the fuel is an issue too, right? Uranium is the common fuel these days, but there are more efficient fuels and safer fuels.
So how does nuclear stuff affect mutations and stuff? Because everyone always says if the nuclear fallout ever happens and they don't survive, they're going to be really mutated fast. That's what every story says.
Well, radiation does have a mutagenic effect.
Yeah, but I don't think it's going to be like as crazy as what.
No,
what most things.
it's more likely to kill than it is to
Yeah.
mutate.
But if something survives, like stuff like, there's videos about fallouts like that happen, and there's going to be like a two-headed deer walking around and everything like that. I don't think that's what happened.
No, if you're presented with the common Darwinism that's taught in biology classes, you need mutations over an isolated population for a long period of time
Where it actually happened.
to differentiate a species. The problem with mutation is most mutations are lethal. The vast majority of them
Yeah,
are
like
lethal.
they're not helpful. They won't harmful to anything.
Yeah.
Yeah.
Anyway, what it does is this radiation that's given off affects the nuclear material of every cell. And when it gets down to the reproductive organs and affects the eggs and sperm, then that affects the next generation.
Yeah, it's important how they come out. And it's gonna be passed on. There are two-headed snakes born though. So
Yeah,
I guess it's normal though.
that happens.
Yeah, there's an actual species that I think they're supposed to be born two-headed.
Well, they're like Siamese twins, aren't they?
Yeah, like they just come out and they have two heads. It's weird. I think
They might have started off as two, or a fertilized egg that split but never quite separated.
Yeah, there's a human born like that too.
Oh yeah.
That can be fun.
What would happen if we didn't have greenhouse gases in the atmosphere? This would be a snowball. The whole Earth would be a snowball.
Ozone layer.
If we don't have greenhouse gases in the atmosphere, then the heat that we radiate would just be gone, and we get colder and colder and colder. And carbon dioxide is the least of the greenhouse gases. Water is much more effective as a greenhouse gas simply because there's more of it.
So you're saying that all the people that says to shut down all the global warming stuff that's going to kill us all?
Yeah, I mean, they don't care if the Earth gets hotter or colder.
They just want.
It's all power, right? They just want power, and that's the way to get it. Okay, so when light hits the Earth, it re-radiates at longer wavelengths, and there's the molecules in the Earth's atmosphere tend to absorb that radiation more effectively than the incoming radiation. That's the greenhouse effect. Now, there is one planet that we know of in the solar system that is a runaway greenhouse. Venus.
Venus, that's what I was thinking.
Venus. Venus has very high carbon dioxide levels in its atmosphere and sulfuric acid, sulfur dioxide and sulfuric acid. And yeah, and plus it's closer to the sun. So it's definitely high. It's hot enough to heat, to melt lead on the surface. Okay.
Just a gas planet.
Huh?
Venus is just a gas planet. As far as
Venus?
I can tell.
No, it's a rock planet, it's like the Earth.
Is Neptune a gas planet? There's a gas planet.
Yeah, Neptune's a gas planet. The giant, the Jovian planets are the gas planets.
Like, we don't know if they're really just gas or if they're surrounded by gas stuff.
Yeah, there's speculation that under those huge pressures, they probably have a rocky core. And then they have a fairly thick layer of hydrogen, maybe some helium. Same composition as a star, actually.
Yeah, just a death planet if you go in a lot of match.
Right. And under that pressure, there's speculation that the hydrogen in down deep is actually a new form of hydrogen, a metallic hydrogen.
Like one we've never seen.
Yeah.
Oh, that's
Yeah.
cool. That'd be so if you add a new element onto it.
Well, it's not a new element, it's an allotrope of
It's
an
just
element.
a new form of it. Yeah,
Form,
I'm just
yes.
saying If we ever discover a new element, it's gonna suck for that. Because that whole thing's gonna be have to be rebuilt.
So new energy sources. I think this is about the last slide. Coal conversion, making gas out of it, right? Takes a lot of the pollutants out. But when you do that, what are you going to do with, you have to extract that stuff like the ash and the carbon. You got to do something with it. So that's really not a solution. Hydrogen, this is the, well, it's not the holy grail, but it's next to the holy grail. Hydrogen as a fuel because you can run it through a fuel cell and produce electricity directly.
Yeah, is that how electric cars are being run as well?
There's lots of work being done on it, yeah, to make hydrogen fuel cells. I remember when the Mercury, Apollo, and Gemini, Mercury, Gemini, and Apollo series spacecraft were developed in the 60s. They used hydrogen fuel cells for their energy source. There are limitations, there are problems. One with the cell and the other is with the hydrogen. How do you store hydrogen safely in a car? It's flammable. I mean, it's extremely
Yeah,
dangerous.
if you crash and the sparks hit it, it's bad.
Energy alternatives. Well, oil shale is producing, that's what we were doing before the Democrats took over. We were fracking like mad. In fact, the US was a net energy producer.
Yeah.
We were exporting energy.
I remember reading about that.
Natural gas is still good, right? Ethanol production from grains is a losing proposition. You have to put more energy into the process than you get out of it. Okay, so that's crazy. It's crazy talk. Methanol, maybe, I'm not sure if it's any better than ethanol. Seed oils, yeah. In fact, the diesel engine was originally designed by, I forget his first name, Air Diesel, the German guy, was designed to run on vegetable oil. Mm-hmm. And then we converted it over to petroleum-based products.
Them gas pumps that have the diesel look so nasty.
Yeah.
There's black everywhere.
Yeah, yeah. Solar and wind,
I remember
they
talking
have
about that
numerous
last week.
problems. Major one is its intermittent availability, right? Cloud cover or the wind stops blowing. In fact, the energy costs in Germany and Denmark now are going sky high because they had this unforeseen calm period in the North Sea where they have a lot of their wind turbines, right? So they got no energy out of it.
So they get a lot for hurricane came by anywhere near there. They wouldn't have to worry about that for a while.
What we need is a better way of storing that energy when they are blowing, when the sun is shining.
So you can use it in the future.
Yeah.
Because we can have a lot of energy if we couldn't store it good.
The problem is the energy density is a real problem. The energy density of wind and solar is just, I mean, it's rock bottom. You gotta take in lots of land.
Well, if we could efficiently use the sun as energy, we wouldn't really have to ever care about energy again.
Yeah. Right.
But that's too hard for us right now.
Or duplicate the fusion process. Yeah.
The process of the sun gets
Mhm. They're still working on it.
Yeah, but that probably won't happen anytime
Not in my lifetime.
soon. Not mine either, problem.
And then it's not just can we do it? Can we do it economically? Right. and preferably without government intervention. Because whenever government sticks its hands in the pie, it just messes things up.
Just forget what happened after that.
And there are also environmental hazards with the production and the disposal of these technologies. Right? They're very polluting when you make solar cells, when you make wind turbines, and then when you retire them, you've got all those pollutants. Right? And there's not always going to be an India and a Pakistan we can send these things to recycle. Right? That's where all our pollution goes now, our electronic pollutions. If we could convince the public and develop safe nuclear energy, that would solve our problems for several hundred years down the line, and make all the green hysterics happy too.
Make all of them calm down.
Yeah,